Welcome to this video on how to determine the gradient or the slope of a straight line, its meaning, and then how to use this mathematical technique to determine the average gravitational constant from data that has been collected from a weight versus mass investigation. So starting off with a straight line, a very simple straight line that starts at the origin where the x and the y value are both 0. This straight line leaves the origin to the right and moves up. Now we have discussed axes before, and so the x-axis is the horizontal axis, and it's an actual fact a number line. And it doesn't only consist of the integers 1, 2, 3, 4, and 5, but has infinitely many real numbers along it. The y-axis is the vertical axis, and so we are going to look at this straight line, which is a relationship of y versus x. But in particular, we want to determine how steep is this graph. So the gradient or the slope of a straight line can be determined by looking at how between any two points, how the rise or the vertical change in the graph compares to the run, which is the horizontal change or displacement of the graph. So let's consider 2 points A and B, but they could have been there, and the other one could have been there, could be anywhere. You could have chosen 0, 0, but we don't want you to do that in grade 8, because what happens is then very often learners, because of 0 doesn't really make a difference to the value, they'll end up only using the x and the y coordinate for 1 point, and we don't want that. So we're not going to allow you to use 0, 0 as one of the points. So let's take these 2 points. We've got A and B. Now, to determine the x and the y values of A and B, what we do is we drop a perpendicular from the point on the line down to the x-axis, and we can see here that the x value of A is 2, and then to find the y value, we drop a perpendicular. In other words, we drop a line that is at a 90-degree angle to the y-axis. And so there we get the y value. So this particular point A has the following coordinates. So the coordinates are, we first write the x value, which is 2, and then we write the y value, which is 1. This is known as an ordered pair in mathematics. All right, so to determine a point on the Cartesian plane is the xy plane, we use ordered pairs. The first number is the x coordinate, and the second number is the y coordinate. Because we are going to be working with 2 points, I'm going to use a subscript 1 for each of these numbers. So it's x1 and y1. That just means that these are the x and y coordinates for point 1, which in this case is point A. Then we do the same for point B. If we drop a perpendicular down to the x-axis, and I'm just going to explicitly put the 90-degree angle in there, you don't need to, just to show that these two lines are perpendicular to the respective axes. Then we get that the x value is 4 and the y value is 2. So we're going to write the coordinates of B as 4 and 2. So that would be x2 and y2. Now what we want to do is we want to determine how steep this graph is. And so we use the following formula. We use that the slope, so I'm just going to use slope, but it's also slope and gradient mean the same thing. all right, that the slope is the rise over the run. Right, so if we are moving between A and B, so let's say, I'm just going to do this. If we're moving between A and B, then the run is the horizontal distance covered between point A and B. That is the run. And if you look along the x-axis, then the run is in actual fact x2 minus x1, which in this case is 4 minus 2, which is 2. That's the run. If we look at the rise is the vertical distance covered along the graph between A and B, and that's the same as the difference between y values, y2 and y1. So y2 minus y1, and in this case it's going to be 2 minus 1. It's going to be 2 minus 1, which is 1. So we can very simply say that this slope is 1 over 2, and that gives us a slope of a half. Now you can write it as 0,5, but we would prefer you to keep it as a fraction, because then it's more explicit as to what's the change in vertical over the change in the horizontal distances. Now, what does this mean? Well, what it means is that at any point along between any 2 points here, no matter how far apart they are, if we had to move along there between those 2 points, then the run, let's say the run was, let's just say that the run was, for instance, a half. Okay. Then if we worked out the rise, if we measured the rise, we would find that the rise would be 0.25. Now, how do we know that? Well, because if you look at 0.25 divided by the 0.5, and you simplify it, you are going to get 1 over 2. And so this is a character or characteristic or a property of this particular graph. Now in mathematics, when you do this later on in the year, you will learn about the equation for this line. It would be y equals m, which is in actual fact, I'm going to actually use blue here, m, which is the mathematical symbol for slope, multiplied by x plus c. Now m is the slope or the gradient, and this is actually an indicator of direction. All right, and the c is what's known as the y-intercept. And the y-intercept is this point here. It's where the line crosses the y-axis. So in order to determine where the graph is going, you actually just need 2 points. You need the point where the line crosses the y-axis, and then you need the steepness or the slope of the graph, and then you can draw the line. So this particular graph has a slope of 1 over 2. How would the graph look if it had a slope of, let's say, 2? All right, so let's say we dealt with a graph that had a slope of 2, and it also then passed through the y-axis, past the y-axis at x equals 0. Well, then we could say, well, if the run was 1, all right, then the rise would have to be 2. So therefore, this point here would be a line on that graph. So this is now for a graph that is a slope equal to 2 over 1. Well, if we draw that line, right, then we'll see that it's got a much steeper. Right, it's steeper than the graph, than the line with a slope of a half. So later on in your studies in mathematics, you'll learn that from this you can actually get the angle between the x-axis and the line from this slope, but you will need to learn a little bit more trigonometry. What if we were dealing with a graph that has a slope not of a half, but let's say of a quarter? All right, so let's say we had a graph where we had a slope of a quarter. Well then, and that it also passed through the past the y-axis at x equals 0. Well, I just would like to say that in grade 8 physical science, we are not going to deal with graphs that don't pass through the x equals 0. So, but in mathematics you will. So, and the reason for that is in grade 8 we deal mainly with what's called direct proportionality, which is relationships where you have a straight line representing the relationship between the dependent and the independent variable. And direct proportionality also requires that the line starts at 0, 0. So we're not going to worry about lines, for instance, that would do this, where they start at y equals 3 on the y-axis. Right, so now let's look at the slope of 1 over 4. Right, so sticking with my convention, my color convention, right, then that means that our, starting at 0, 0, our run would be 4, and our rise would be 1, which would take us to that point. And so then we would land up with a line that goes through the point 4, 1. And so you can see that that line is much less steep than the line that's got the slope of a half, and certainly that has less steepness than the line that has got a slope of 2 over 1. So this is a very important mathematical technique that we have learned, and what I have done up thus far is to purely look at this technique in the context of, not actually in a context, but in a physical context, but purely as a mathematical technique where the y and the x are just general variables, not representing physical quantities. And so this is how you will learn slope in mathematics. But this is physical science, and so what I want to do now is I want to move on to how we will use this technique in the context of physical data. So let's consider the following problem. Plot the following data points and use the graph to determine the average gravitational constant G bar. Now, just whilst we're looking at G bar, G here stands for the gravitational constant, and the horizontal line on top of G, that represents, we call it the bar, B-A-R, and that represents the average value for the constant. Now the values that we have here are recorded from a hypothetical experiment that was done. In the left-hand column, we have the mass values, and the symbol M represents the quantity of mass. There's a division line, and then there is, in brackets, is G. Now don't confuse this G with that G. This G is in the context of a unit, so that's grams. And these values, 95, 200, 250, etc., were the mass measurements made in the experiment, and each of them was in grams, but we are going to represent them on a number line, on an axis. And so we are going to divide each of these values by the unit to produce a pure number. That's why we have divide by grams. It also serves to explicitly show that this mass, these quantities, were measured in grams. We do the same for weight. Weight divided by newtons. This implies that all of these values were actually measured in newtons. Now, we did this in class a few times, and before we go further, I would like to just point out a few things. So we are going to plot weight versus weight in newtons versus mass, right? Now the mass we're going to plot on the horizontal axis, right? And we are going to get a straight line, as we got in class, which starts at the origin, and we are going to identify 2 points. Let's call them point A and point B, and we are going to determine x1 and x2 and y1 and y2, and x1 and y1, those are the coordinates for point A, and x2, y2, those are the coordinates of point B. But x1 is in actual fact going to be a mass measurement, and the same is true for x2, so we can call them mass 1 and mass 2. And y1 and y2 will be weight measurements, so we can call them weight 1 and weight 2. We are then going to determine what the rise and the run are between points A and B along the graph. So the run will be the horizontal change in position, or the horizontal distance between A and B. So that's going to be x2 minus x1, and the run is going to be, sorry, not the run, the rise is going to be y2 minus y1. All right, so now we're then going to work out the slope, or the gradient, and we are going to use the slope in order to determine the average gravitational constant. All right, so it's going to be rise over run. The rise is going to be y2 minus y1, and the run is x2 minus x1. Remember, between the 2 points, A and B, the run is the horizontal distance covered between A and B. So it's x2 minus x1. That's the run. The rise is the vertical distance covered between A and B, and that will be y2 minus 1, y2 minus y1. And the slope is the ratio, is the comparison of the rise over the run, which is y2 minus y1 over x2 minus x1. All right, now we learned that in order to get the average gradient, the weight would need to be in newtons, and the mass would need to be in kilograms, because the average gravitational constant is measured in newtons per kilogram. But our data here, the mass is not measured in grams, in kilograms, so it's measured in grams. So we need to convert it to kilograms before we plot the graph. Now, it's true, in class I allowed you to plot it in grams, the mass in grams, but then you found that afterwards you had to do, with the slope calculation, you had to do an inconvenient, uncomfortable conversion in the slope calculation from grams to kilograms. So my suggestion is rather that before you plot the graph, that what we do is that we do the conversion from grams to kilograms in the table. So now we're going to convert mass in grams to mass in kilograms. Now, 1 kilogram is 1,000 grams. The word kilo means 1,000. So if we divide both sides by 1,000, then we get that 1,000th of a kilogram equals 1 gram. So what that means is that if we want to go from grams to kilograms, then we need to divide by 1,000. And if we want to go from kilograms to grams, we need to multiply by 1,000. You will do more on conversions in grade 9, and not just with grams and kilograms, but with other quantities as well. Now, this means then that to go from grams to kilograms, we must divide by 1,000. Going this way, we must divide by 1,000. So now our mass values are going to be as follows. 95 divided by 1,000 is going to be 0.095. 200 divided by 1,000 is going to be 0.2. 250 divided by 1,000 is going to be 0.25. 380 divided by 1,000 is 0.38. 500 divided by 1,000 is 0.5. And 650 divided by 1,000 is 0.65. So now we have our mass in the correct unit for us to be able to extract the average gravitational constant from the graph once we've drawn it, without any complicated conversions in the slope calculation. And so now we're going to take this data and we are going to plot it on a piece of graph paper, and we're going to plot a weight versus mass graph. But maybe before we do that, let's just talk about the format of tables. In physical science, we, as a rule, the first column is where we record our independent variable values. And the independent variable is what we plot on the x-axis or the horizontal axis. The independent variable is that quantity which the experimenter or the investigator can directly control. Now, I must be careful when I say control, because we talk about control variables where you can fix the variable. Let's rather say the independent variable is the quantity which the experimenter changes directly. So in this case, the experimenter chose objects, specific objects that had specific masses. So he or she changed the mass directly. The weight is dependent on the gravitational field and the mass. And so the weight was not directly changed or altered by the experimenter, but was dependent on what the mass was, and of course the Earth's gravitational field. If it's on the Earth, in this case, no, it's not necessarily on the Earth. All right, this is a hypothetical experiment. We're actually going to see that this can't be directly on the surface of the Earth, because the gravitational constant here is not going to be 9.8, which is the average value for gravity on the surface of the Earth. You're going to see that it's a lot less. So either this experiment was done very high up above the Earth's surface, or it was done on a hypothetical planet which is much smaller than the Earth, as you will see. The weight was therefore the dependent variable, and therefore it's going to be plotted on the y-axis. Right, we've altered the unit for the independent variable, so we're going to plot the mass in kilograms column and the weight in newtons column. But just to reiterate, to revise, when you get a table in physical science, your left-hand column is the independent variable and the right-hand column is the dependent variable. And one other thing is, if you put the units with the actual values in the table, a mark will be deducted, because we want you to explicitly put the units in the heading of the table. So now let's move on to us actually physically plotting this data and then determining the average gravitational constant by working out the slope. So in your exam, you are going to be given a piece of graph paper that looks like this. I would suggest that you draw your graph in landscape, where the shorter side of your graph paper is on the vertical and the longer side is on the horizontal. There's nothing stopping you from doing it the other way around, but in portrait, but I prefer landscape. And then we start with firstly with the title. So we are this is going to be a graph of the dependent variable, which is the weight, versus the independent variable, which is the mass. So for that you would get a mark. Graph of weight versus mass. Then on the vertical axis, we are going to draw the dependent variable axis. All right. So you would use a ruler. Okay. And so what we're going to do there is, I'm just doing it in blue, just so that you can see that I am plotting these values, but in your exam you don't have to use color. Right, so along there, this is where we are going to plot the weight. We must label the axis together with the unit. So for there's a mark. All right, look at your biggest value. Your biggest value is 2000. Right, it's important to be able to determine a scale. So we count here, we see, okay, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. To be able to represent 2000, that's the maximum value of weight that was recorded. I would suggest we use a scale where each of these blocks represents 200. Then 200, 400, 600, we'll get to 2000 on that scale. So now we go and we say, all right, this is 200, this is 400, this is 600, this is 800, this is 1000, that's 1200, this is 1400, this is 1600, 1800, 2000, and normally it's good to go a little bit further, 2200. Now it's very, 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 very important that you have a consistent scale on an axis. Each of these blocks must represent 200. You can't have the first block representing 800 and then the rest of the blocks each representing 200. You'll get penalized for that because it's an inconsistent scale. We don't cut scales like in life science. In life science, they've got a different convention for doing graphs, which is totally fine. In physical science, this is our convention. You must have consistency of scale on an axis. So for that, you get another mark. So your scale gets a mark. So already there's 3 marks. 1 mark for the heading, as you can see, graph of dependent variable versus the independent variable. Right, now on the horizontal axis we are going to plot the mass. Now you'll see here that this is in actual fact wrong. This is not weight, this is mass in kilograms. Alright, so we're going to use yellow. Alright, so we're going to, here, we are going to plot on this axis the mass. Right, and we put in the mass in kilograms. and there's a mark for that. And remember, don't just put don't label your axis just with the quantity. It's the quantity and the unit. If you only put the quantity, you don't get the mark for the label. We need to represent up to 0.65, right, which means we can have a scale, we can have a big scale. Okay, what I mean by that is 1 unit can represent a large value of the quantity we're representing, which in actual fact is a small scale, because it's 1 over a big number is actually small. But to keep it simple, that 1 unit on that 1 block represents a large amount of mass. So if we count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, you can see that we can actually fit the 650 easily. Now, the trick is to also try and get your graph to be as big as possible, because the bigger your graph is, you're going to make mistakes with plotting. But if you make mistakes because of you using a physical pen or pencil, if the bigger your graph is, the smaller percentage error you make. So the rule of thumb is just try and make your graphs as big as possible. Don't make your graph so that your graph only fits into a little part of your graph paper like this. Try and use as much of the graph paper as possible. So we've got to go up to 0.65. So if I did 1, 2, 3, 4, 5, 6, 7, then we'd only use this part of the graph. So let's double it. Let's make that 1. So we make 2 blocks 1. Right, so we go in here and we say, okay, let's make that 0.1, this 0.2, this 0.3, this 0.4, this 0.5, this 0.6, and this 0.7. Sorry, my notes are looking a bit like 6s. Right, now that means in between, this will be 0.05, this will be 0.15. Okay, so that's the halfway points. Now you get another mark for that. Note that that each block on the y-axis represents 200 newtons, but each block on this axis represents 0.05 kilograms. So the scales on the 2 axes don't need to be the same. Like in mathematics, it's generally like that in math. But in physical science, the scales can be very different. But the key thing is that whatever your scale is, you must ensure that each of these blocks represents the same amount of your quantity. So one of those big blocks represents 0.05, 0.05, 0.05, 0.05, 0.05, then it's fine. So there's another mark for that scale. All right, and so we have now that we have that already before even drawing the graph. We have 1, 2, 3, 4, 5. Now, I'm just going to let you know that if you don't attempt the graph, if you just do this, then you don't get any marks. All right, you have to plot the data. Even if you plot it wrong, you must attempt to plot this data on here in order to get these marks. All right, so now let's plot the data. So we are going to do that, and we say, okay, firstly we're going to plot 0.095 and 290. So 0.095 and 290. So this is 0.09 is there, so 0.095 is there. This is 300, halfway between 200 and 400, and it is 290. So 290, if this is 300, then 290 is going to be just underneath there. So this is how we're going to plot the point. We put the dot there. And then remember in class I mentioned that every data point has got error in its dependent and in its independent variable. Now we use what we call uncertainty bars or error bars, but in grade 8 we're not going to do that. What we're going to do is we're just going to represent that point with a circle of uncertainty around it. Okay. All right, so I'm just going to put it there for the time being. This is called the circle of uncertainty. Okay, that's just good scientific practice. Circle of uncertainty. Right. Okay, I'm not going to leave it there. I'm going to take it out. All right, so that's the first data point. All right. So now we are going to plot the other data points. So we've got 0.2 and 780. So 0.2 and 780. So we've got 0.2 there. My apologies for the skewed line. Let's go here, 0.2. This is 700, so 780 is very close to 800. So there's our next data point. We're going to do these pretty quickly. You've got 0.25 and 740. 0.25 is here. 0.25 is here. And 740. All right. And so this is 700. All right, this was 780 here. So 740 is actually lower. All right, so we have a point here. It seems a bit weird, but we'll discuss this point a little later. All right, 250, 740. Then we've got 0.38, 1250, 0.38. So 0.38, this is 0.35, 36, 37, 38. Okay, there's 0.38, and it was 1250. So this is 13. So 1250 is in the middle, so we plot it. And so our data point there will be that. All right. And then we've got 0.5, 1450. 0.5, 1450. So 0.5 is easy. There's 0.5. It's along that line. 1450. Apologies for that. Here we've got 15. 1450 is here. 1450 is here. All right. And so there is our point. And then last but not least is 0.65, 2000. So we've done that one, that one, that one, that one, that one. We're now going to do 0.65, 2000. So 0.65 lies directly between 0.6 and 0.7. So it's along that line. All right. And 2000. 2000 is along there. And so there is our data point. All right, so I might have, maybe should have just gone a little bit further in. All right, it should be there. All right, where the two lines intersect. All right, so we've plotted those points. Now for plotting the points, there's 3 marks for plotting the points. All right, so plotting the points is really important. And so now what we're going to do is we're now going to draw the line of best fit. Now the line of best fit is an average line, which represents the average relationship between the weight and the mass in this case. So later on, as you go further in science, you'll see that your data isn't always best fit by a line. It's sometimes best fit by a hyperbola or by a parabola. But that's for more complicated relationships, not in grade 8. So we take our line, all right, we know for a fact that when your mass is 0, when the object's mass is 0, it means there is no object. So the weight will be 0. Right? So we now draw starting there. All right, if you drew that line, that would not be a good representation of the data. If we drew that line, that would not be a good representation of the data. So what we want to try and get is you want to try and see, okay, if we can get an average line. Now, an average line does not need to go through all the points. It does not need to go through any one single point, maybe 0, 0, yes, because we know that if the mass is 0, there's no weight. So I'm going to draw my line of best fit like that. Now your line of best fit will be different, and there will be error in it. There's undoubtedly, there will be error. But this method averages out errors, and yes, at the end we still acknowledge the fact that there is an uncertainty in the value, but it gives us a good indicator. Now, sorry about that. What I want to do now is I want to just point out, you see this point here. This point seems to be out. I said it was that point, but it wasn't that point. If you look at the general trend, can you see this point? Something weird is going on here. We have a name for this point. We call this point an outlier. An outlier, O-U-T-L-I-E-R. Now, outliers, either there's something exceptional happening there, which if you can explain, and it might be something new in physics or chemistry, and you might end up getting a Nobel Prize, or it's just because a big error was made in the experiment. Maybe whilst this person was making the measurement, someone came past, tapped them on the shoulder, smiled at them, and put their finger on the scale. That outlies there, in this case, due to error. All right. So in the exam, you might be asked, given a lot of data, and asked, okay, what is the outlier? The outlier is that point, or is a point that completely is out of sync with the rest of the data. All right. Now we want to get the slope. So what I'm going to suggest you do now, we've been going for quite a while, is to pause the video, go and get yourself a cup of coffee or a cup of tea or orange juice, and then come back and let's do the slope together. All right. Welcome back. All right, so what we're going to do now is we are going to choose 2 points. Okay, and I'm going to choose 2 convenient points. Ooh, this looks like a lovely point. This point here, and I'm going to use a square bracket. Not square bracket, a square as a region of uncertainty. I choose that point because can you see it lies on 2 nice bold lines. It's easy to recognize what point A is. I'm going to call it point A. Okay, point A, there's point A. A is going to be 0,2, okay, and it's going to be 600. 0.2 and 600, and that's going to be x1, and that's going to be y1. Can you see? 0.2, 0.2, and 600. I could have chosen that point, doesn't matter. I've chosen A because it's nice and easy to read off the graph. Let's see if I can find another one. Yeah, there, I found another one. All right, I found another one right there. All right, you could choose other points if you want. So that's point B. If you look at B, if I go down here, that's point 4. All right, and if I go along here, it's 1,200. 0.4 and 1,200. All right, and this is x2 and this is y2. All right, so we have those 2 points, A and B, and we are going to use A and B now in order to find the average gravitational constant. So what we do is we write down the average gravitational constant, and this is important, is the slope. All right, and we are going to use the slope as rise over run, y2 minus y1 over x2 minus x1. All right, by the way, in mathematics, they use m equals y2 minus y1 over x2 minus x1, and that m is not the mass, that's the symbol for gradient in mathematics. Now, if we look at the points here, y2 is 1,200 and y1 is 600. So this is going to be 1,200 minus 600, but remember these are physical quantities, and so the 1,200 is on the weight axis and the 600 is on the weight axis. So The unit for 1,200 and 600 is newtons, right? And then the x values, which in actual fact are mass values, are comma 4 for x2 and comma 2 for x1. So it's comma 4 minus comma 2, and remember the kilograms. Now if you had left this as 400 and 200 grams, here is where you would have to have done a conversion. All right, but we've already done the conversion. So now we work it out and we go, okay, this is cool. So this is going to be upstairs, 1,200 minus 600 is 600 newtons. Downstairs, comma 4 minus comma 2 is comma 2 kilograms. All right, so now we work out what the average gravitational constant is, because 600, and you're allowed to use a calculator, yeah? All right, 600 divided by, and I'm just going to do it manually, 2 over 10. All right, you're going to be asking, why are you doing it manually, Mr. Duffield? Well, I'm doing it manually because I haven't got my calculator with me. So 600, and we tip and we times, so that's 10 divided by 2. All right, so we're going to get that this is in actual fact, if we look here, 600, 6,000 divided by 2 newtons per kilogram, right? And so G is 3,000 newtons per kilogram. Now the mark allocation for that would be as follows. There would be a mark for identifying or choosing specific points on the line of best fit. I have also yet to mention that the actual line of best fit, what I call the LOBF, line of best fit, would get 2 marks as well. And yes, there's uncertainty in it, but still the method, you get the marks if you do it reasonably well. So you get a mark for each of the points that you've identified that you're going to use. And once again, note, we didn't use any of the data points because these points should actually be better points, more accurate points than any of your data points, because the line averages out the errors. So it's critically important that you don't use existing data points. Now, there's a mark for the general slope formula. There's a mark for the change in y over the change in x, the substitution step, and there's 2 marks for the substitution step, for the upstairs and the downstairs. There's a mark for the final value, and there's a mark for the unit. So if you don't put the unit in, then you lose a lot of marks. So if you look here, you'll see that the graph is 1, 2, 3, 4, 5 for the heading and the axes being labeled and having good scales. Then 3 marks for the plotting of the data. And please don't plot the data just with a cross or a little dot. A dot with a circle of uncertainty around it. All right, and then 2 marks for the line of best fit. So that's 10. 10 marks for the graph. Then 1 mark each for the points that you have chosen and that you've clearly labeled. And then for your calculation of the gradient, there's another 5 marks. So it's 1, 2, my apologies for that. It's 1, 2, 3, and then 4, 5. Yeah. So in total, what we've done is amounts to about 17 marks in your exam. So this is a really important part of your exam. Just something interesting is that if you look at this G value, remember I said that you would see that this was probably on a planet that was smaller than the Earth. Well, I had it wrong, because in actual fact what I was doing is I was looking at the ratio between the weight in newtons and the mass in grams. Now, I saw it as approximately about 3. Now, the Earth's gravitational constant is about 9,8. But in actual fact, because the mass was in grams, there was a hidden factor of 1,000 there. We had to divide by 1,000, and dividing by 1,000, if you divide weight by mass, and you're dividing by 1,000, dividing by a quantity that needs to be divided by 1,000, in actual fact it means you're timesing by 1,000. Look here, let me show you. If you look here, can you see that here, if this was 200 grams, 600 divided by 200 grams would have been 300 newtons per gram. Then dividing by 1,000 in the denominator means I have to tip and times, and would make it 6,000 over 2. And so in actual fact, this gravitational constant would be on a very extreme planet, all right, or star, because this value is much bigger than the value of 9,8 newtons per kilogram on Earth. And so we would probably find that this is on a planet or a star that has a massive mass. All right, and you get stars that are many times bigger than, millions of times bigger than our sun, which is more than 1,000,000 times bigger than the Earth. So there are places in the universe where the gravitational constant is even bigger than this. But that's for you later on, to encounter later on in your studies in science. So I hope that this video has helped you. It's quite a long video, but if you consider the fact that this section is that we've just done, is about, an exam is about 20 to 23 marks out of an exam out of 90, then it's been worthwhile to focus on this. So keep on practicing, and I have no doubt that this will pay dividends in your exam. Goodbye.